happened to everybody? Just dropping out. What time do you have? I'm going to watch.
2 minutes.
2 minutes after? No. I got 4 minutes after. I get my watch is too fast. Okay. Well, we'll get started anyway. So, if you remember last time, we started talking about the Bayes minimum mean square error estimator with a linear model. So let me just remind you what that was. Okay. So the idea here was that you had a model of this sort, y equals hx plus w, and this was zero mean with some covariance CW and expected value equal to 0. And the data x, the vector x also had a covariance which we call Cx, and x and w were uncorrelated. Okay. So from this, we wrote down the minimum mean squared error estimator for this linear model based on this given data was mx plus h transpose CW inverse h plus Cx inverse h transpose CW inverse y minus h times mx. Okay, so the best estimate in the minimum mean squared error sense was given by the mean of x and then a correction term, which is this guy here. So this whole term is basically like a gain, and this is the deviation of that estimate mx. So this might have been the estimate if you didn't have any other information. And so this is how good that estimate was and a correction factor applied to it. Okay, so then we talked about another type of data processing problem where the measurement now is basically of the following sort. So suppose you have x of n equals s of n plus noise. So here, x this time is your measurement. And we wanted to see if we could predict all the values of s from the measurements, if we could predict just one of the values of s from the measurement. And these gave rise to various different types of problems, which we called filtering and smoothing and prediction and interpolation and so on. So what I want to do today is discuss these problems in more detail. In particular, I want to talk about the smoothing problem. So the smoothing problem is you're given x of n. So let's say you're given a vector x. Let's call it x0 through xn minus 1. Okay? And what you would like to do is to estimate s, which is, so let's transpose s of 0 through s n minus 1. Okay, so this is your unknown parameter vector, if that's what you want to call it. Okay. Now, what we know about these variables is we know some statistics of s, and we know some statistics of the noise. And so from this, we're going to try to find the best estimator in terms of, in this sense, in the Bayes linear minimum mean squared error sense. Okay, so let me remind you the autocovariance function, this for any random process Rxxk. So we're assuming that these are white sense stationary processes, which means that the autocovariance function which is defined as expected value of x of n times x of n plus k, that this thing depends only on this difference between the argument of this x and the other x. Okay, so the correlation between any two terms is only dependent on how far away those two terms are in time. Okay, so with this in place, then the covariance matrix for this particular random process would also be of the following sort. So these terms would basically end up in here, and of course along the diagonal you would have, you know, Rxx 0, Rxx 0, Rxx 0. Because if you let k be equal to 0, then you have the expected value of x squared. And along the off-diagonal terms, right, Rxx 1, Rxx n minus 1. Okay? And of course, this is going to be a symmetric matrix, so here you have to have Rxx 1 and so on, Rxx n minus 1, etc. Okay, so with these definitions in place, let's talk about, I mean, for this case, I'm assuming that the expected value of x is equal to 0, because otherwise this would not be exactly the definition of the covariance, of course, because then you would have to subtract the expected value of x squared from that. So for the time being, let's just assume that the expected value of x is 0. All right, so now the smoothing problem, remember the model was x equals s plus noise. Okay? So now if I wanted to write down the autocovariance function for x, so Rxx of k, so remember this is expected value x of n plus k. Okay, so if I plug in the various different terms in here, so x of n is s of n plus wn times s of n plus k plus wn plus k. Okay? Now I'm going to multiply everything through and simplify various things. And what I'm going to notice is that I'm going to have an expected value of s times s of n plus k, which is basically going to be the autocorrelation function for s. Okay? So this is, once I simplify, this is going to be Rss of k plus Rww of k. So these are the autocorrelation functions for w and s. And I assumed that s and w were uncorrelated, so there's no cross-correlation function for w and s. Okay, so this is the way it works out. So correspondingly, if I write the covariance matrix for x, this is going to be covariance for s plus the covariance for the noise. Because I'm just going to take these terms and stack them into a matrix. Okay? All right. So now, what I want is the Bayes linear minimum mean squared error estimate for S. So this would be S hat. Okay? So if I go back and think about what the formula for this was, this would be CS times CX inverse times X. Okay? But then this CX is given by this quantity. So my estimate would be S hat is CS times CS plus CW inverse times X. Okay? Let me talk about where this here comes from. So if you look at C of Sx, okay, so this is the expected value of Sx transpose, right? Which is the expected value of S times S plus W transpose. Okay? So if you look at this, this is the expected value of SS transpose. plus the expected value of SW transpose. But this guy is 0, so this is just SS, or just CS. Okay, so that's why this ended up here. So what this says is, in order to find the Bayes linear minimum mean squared error estimate, what you need to do is to find the covariance matrix for the signal and the noise, and by combining these two in this fashion and multiplying by the data vector x, you're going to get this estimate. Okay. This matrix here, this CS times CS plus CW inverse is called the smoothing matrix. So we'll see why this is called this, well, we know why it's called the smoothing matrix, because this is the problem that we call smoothing. But we'll see another interpretation of this in a short while. But let me just kind of mention very quickly, if you think of CS as being the variance of the signal, right? Let's just think about everything in terms of scalars. Okay? So think of this as a variance of the signal. So this is the variance of the signal divided by variance of the signal plus variance of the noise. Right? Now divide everything by the variance of the signal. So let me write it in scalar fashion so you get a rough idea. Okay, again, this is not a general result, it's just an example that I'm using. So as an example, let's say CS is just sigma squared S. And let's say CW is just sigma squared W, right? Okay, so this matrix here would be like sigma squared S divided by sigma squared S plus sigma squared W. Okay. And so if you rewrite this by just dividing everything by sigma squared S, you get 1 over 1 plus sigma squared W divided by sigma squared S. Okay. Another way to write this is this quantity here is 1 over the signal to noise ratio. So this is 1 over 1 plus the SNR to the minus 1. Okay? This turns out to be basically the expression for what's classically known as the Wiener filter. Okay, now here, what you have is a general matrix formulation for it, but typically this, we'll write this in the frequency domain, for example, and what you see is that this SNR will end up being computed at every frequency for the time domain signal. And so the interpretation of this will be a little bit more clear as we go on. Okay. So this is just an example to show you what this means. Okay. Yeah.
Can you show a couple pages back?
There's only one page back, so. Is that what you mean? Or?
Yeah. So you make the assumption that the expectation value of S is 0?
The expectation value of X is 0.
Or I mean,
are you talking about here? Yeah, so I'm assuming the expectation of W is 0 and expectation of X is 0, so expectation of S must be 0 too.
Okay.
Okay.
That's what this is. Okay.
Right. Okay, so this was for the smoothing problem, which is you've got all the data and you want to estimate all the signal positions. Okay? Now let's see how the problem changes if you just talk about the filtering scenario. And the filtering scenario is all you want is to estimate one single value of the signal given all the data that came before it. So the signal measured is x0, x1 through xn. And what you want is the signal corresponding to this position, Sn, which is a scalar, let's say, and this is unknown. And then what you're going to do is you're going to repeat this process for every n. So you're going to go up to n, you're going to estimate this n, this s of n, and then you're going to go to the next data point, you're going to estimate the next s, and so on. So this is what you call a sequential estimation problem, as opposed to a batch estimation problem, which this smoothing was. It turns out you can actually get the smoothing solution by doing a bunch of sequential estimations. I think I mentioned that. You go in forward in time, and then you go backwards in time, and you get the same answer. Okay, so this is then the unknown that we're looking at, and we're going to assume that this n goes from 0 to n minus 1, and we're going to repeat this process for every n. Again, we have the same scenario as before, namely the covariance of x is the covariance of s plus covariance of w. And so this is our unknown parameter, c theta. And now if I compute c theta x, remember, in order to do the Bayes mean squared, I need to find the correlation or the cross-covariance matrix between the unknown and the data, right? And so this is the expected value of s of n times x of 0 through x of n. Okay? All right, and then x here is s of n plus w of n. So I can rewrite this as s plus w, and then multiply everything through. And what I'm going to get is expected value s of n times s of 0 through s of n. Okay, the w goes away because I've assumed that s and w are uncorrelated. Okay, does that make sense? All right, so then if you write this in longerhand by just multiplying this s through, what you see is that this vector here, this expectation is going to be a vector, right? So it's going to be RSS of n, comma, RSS n minus 1, and RSS 0. Okay. The definition of the autocorrelation function was you take the two samples of the random process, you multiply them, and the quantity that you get, depending on how far away these two samples are, gives you the value of the autocorrelation function. So here, these two samples, Sn and S0, are n apart, right? So their difference is n, so this becomes RSS of n. The next two are n minus 1 apart, so this becomes RSS of n minus 1. And these two are not apart at all. They're at the same position, so this becomes RSS of 0. Okay. So this basically becomes a vector which, if you remember from the previous slides, it basically looks like one row of this vector, of this matrix, except that it's for S, not for X. Okay? So let's call this RSS as a vector. Let's call it prime because it's kind of reversed in time. Okay, so this is just the name I'm giving it. Okay, so with this, then the estimate S hat of n at that particular position that I was interested in is going to be this RSS prime transpose times CS plus CW inverse times X. Okay, so this part is exactly the same as before. It's exactly the same as this. The only thing that's different is that this CSS is just one row, and this was all the rows of the matrix. In fact, what this is the last row of that matrix, right? Just like I showed you. It's basically the last row of this matrix. Okay. Okay, so what this looks like, you can think of this as a linear filter, right? So this is just a vector. Let's call it A transpose X. Okay, and the A is CS plus CW inverse times RSS. And this is now a single vector that multiplies this x for each sample S of n. So you can think of this as a filter that actually evolves over time for each S of n that you're going to estimate. Okay? I want to make sure this is clear before I go on. So if it's not, please ask a question now so that I can help you understand it better.
Okay, so RSS is more or less a weighing function?
RSS is basically a weight function, that's right.
Then how does, or I guess what's the interpretation of CS plus CW inverse?
CS plus CW inverse is the covariance of X.
Right.
Okay? So what this is basically a matched filter.
Right, but that's more or less like another weighting function. So
That's right. This whole thing is a weighting function. So you're weighting the different elements of X in order to get an estimate of S hat. But if you want to look at this whole thing here, what this is this guy here is CS plus CW is the covariance of X. So this term here, CS plus CW inverse times X, essentially does some kind of whitening on X. Okay? And then it takes that whitened version and then it correlates it with the autocorrelation function of S. The point is, in order to estimate this S hat, you don't know, of course, what S hat is. What you do know about it is you know its autocorrelation function. Okay? So what this does is it basically computes a weighted version of the elements of X according to the covariance of those elements and the autocorrelation function for the signal that you're looking for.
I'll ask you offline.
Okay? So the basic idea here is that these are just, I'm just simply plugging in what the formula is for the for this scenario. Okay? I mean, if you just take this scenario and think about this as M is 0, H is identity, X is replaced by S, then you get exactly everything that I wrote down here. Okay? So just take what I wrote, X equals S plus W, right? So W is the same as W. S here is taking the place of X, H is identity, and X is playing the role of Y. That's it. Everything else is the same. Okay, so if you understood that part, then you will be able to understand this offline if you look at it one more time.
I'm just trying to get the, I'm trying to make some kind of physical interpretation if it's possible.
Well, the interpretation really is that you're computing, in order to get an estimate of S hat, you're computing some kind of, you're correlating the value of X with the autocorrelation function of S. You're saying, I know the two are somehow related. Okay, so what this is telling you is that the estimate of S is a linear combination of the elements of X up to the point that you're looking. And that specific linear combination is decided upon by how much uncertainty there is in X and how much you know about S. That's about as good a physical interpretation as I can give you.
Okay.
Okay, the important thing to remember is that this here is just a time-varying filter. Now, what I mean by a time-varying filter is that if you look at the definition of this RSS, it's just a vector that goes from n to 0, right? Okay, so if I now go to the next data point, what's going to happen is that the coefficients of this filter are going to change, right? So every time I'm estimating S hat, I'm coming up with a new coefficient vector A to multiply by the data up to that point. So this whole thing really is a is a time-varying filter. So the data is coming in here. Here's the output of the filter is S hat, and the input is the sequence of data x of 0, x of n. Okay? but the impulse response of this filter is changing. And it's changing not in an arbitrary way, it's changing according to the input, right? And according to what you know, which is this term here. Okay, so let's see if we can be a little more specific about what the impulse response of this filter is. So what I'm going to do is I'm going to write this S hat. I'm going to write this expression here in a slightly different way. I write S hat of n is the sum k equals 0 to n hn k times x of n minus k. And so this h is what I'm going to call the impulse response. This is just a convolution. So this is the impulse response of this filter that I just wrote down here. So this k is just the index from 0 to n, and this n here is trying to demonstrate that this impulse response actually changes, right, for each output value according to this formula. Okay, so let me rewrite this equation in terms of this notation and try to show you what this impulse response in fact is. So suppose you wanted to implement this whole thing and produce an optimal estimate of S hat of n in an ongoing fashion, right, from one point in time to the next. How would you do that? Well, what you would have to do is, given the autocorrelation functions that you have, you would have to estimate what this is. You would have to solve for what this is, and then plug it into this filter, and then run this filter forward in time. Okay, so how do I come up with this impulse response given that I have this expression? It seems simple enough, but we have to solve an equation in order to get the impulse response directly. So if you write, if you compare this equation to this equation, what you have is you have CS plus CW times H, and this H is a vector that I'm going to define in just a second. This is RSS. So let me write H. Here is H of 0, H of 1, H of n, and I'm going to index this. The notation gets a little bit ugly here because this vector, actually the elements of this vector are going to change for every point in time, so I have to index this somehow by n. Okay, so this vector here is the thing that I'm interested in, and this is the equation that I need to look at. And RSS here is not exactly the same as the RSS prime. It's actually a flipped version of it. So this RSS is RSS 0, RSS and transpose. Sorry, there's a transpose here too. Okay? So if you now take a look at these, if we set them up into this equation, what we have is RXX 0, RXX 1, RXX n, and then RXX 1, RXX n, RXX minus 1, and let's see, RXX minus 1, RXX 0. And the vector H is going to be in here. And this is going to be equal to RSS 0, RSS 1, RSS n. Okay? So here you have the autocorrelation function for x. Here you have a vector, which is the autocorrelation, one vector containing the autocorrelation functions for S, and here's the H that you need to solve for. This set of equations has a famous name. It's called the Wiener-Hopf equations. The idea is that you have to solve this equation every time, right? For every n, you have to solve this to get the impulse response of the filter you're interested in. And that seems like kind of a nightmare, right? It's a big equation. I mean, suppose your n here is 10,000, right? So you've got 10,000 by 10,000 impulse response that you have to solve for. And you have to do it every time. Now, people don't do it every time. There's been a lot of work that's been done to try to increase the efficiency of this process. And although I won't talk about it in much detail, there's something called the Levinson-Durbin recursion. And this basically avoids solving the equation every time. Essentially what ends up happening is you establish a relationship between this h for a time n and the h for time n plus 1. And then you carry that recursion forward in an algebraically very efficient way so that you don't have to actually solve this equation again and again for every time instant. And there's a whole lot of literature on this, which if you're interested in, I can certainly point you to. All right, so now let's take a look at what happens if, in fact, this n is infinitely long. Right? So let's say, I should say, let's assume that the data is infinitely long. Okay? So you have data going from minus infinity to infinity, and you've got one point of the signal that you're trying to estimate. So suppose you have data going all the way back, and then x of minus 1, x of 0, x of 1, and then going all the way forward. Okay? And still, what you're interested in is to estimate, you still want s hat of n for a particular n. Okay, so you have an infinite two-sided stream of data, and you want s hat of n. Now, if we go back and take a look at this, what this is going to mean is that now, instead of estimating based on just the past data, you're going to estimate based on past and future data all the way out to infinity. So this equation would now become, this is a finite impulse response filter, right? It's got a finite number of taps. Now what's going to happen is that this filter is going to become an infinite impulse response filter. So now you would have k equals minus infinity to infinity, hk, x of n minus k. Right? Now this h of k, being an infinite impulse response, is just one function, and it is time invariant. Okay? So now this becomes a time invariant infinite impulse response filter. So now you could ask yourself, okay, if this is now a time invariant filter, can I implement this, or can I understand what it means in the frequency domain? And it turns out the frequency domain interpretation of this is a classical result, which is basically the Wiener filter, which explains the name for the equation that I showed you before, namely the Wiener-Hopf equations. So if you wanted to write these Wiener-Hopf equations now in the case where you have an infinite amount of data, then this matrix would just be an infinitely long or infinitely big matrix equation, right? So instead of doing that, let's write a tight sort of convolution version of it. And what would happen is this. You would get k equals minus infinity to infinity, h of k, rxx, say L minus k, and this is equal to rss, rss, k, and this is for all L. Okay, so basically what I'm doing is I'm writing every row of this in terms of an infinite set of equations. And so I have one equation for every row, and they look like this. Okay. Now if you look at this left-hand side, what this is, it's simply the convolution of this infinite impulse response with the autocorrelation function for x. Okay? And the right-hand side is the autocorrelation function for s. So if I write this in the Fourier transform domain now, if I take the Fourier transform of this, I get the power spectra. So this becomes h of f times pxx of f equals pss of f, where these are now the power spectra of x and s respectively. Okay. Okay, so let's write this in a slightly different way. Remember, what we're interested in here is we want to find out what this guy is. We want to find out what the impulse response of this filter is. So now if you rewrite this, you have h of f equals pss f divided by pxx f. And write this again, pss f. pxx, remember x is equal to s plus w. So its power spectrum is the sum of the power spectra of S and the noise. Okay, because S and W were uncorrelated. Okay, so now you have this. Now we can divide this by PSS, 1 over 1 plus PWS. PS F, and now this is 1 over 1 plus signal to noise ratio inverse at every frequency. Okay, and this exactly is the Wiener filter. What it's doing is it's basically telling you at places where the signal is strong, what you're going to do, what it's telling you is that the impulse response of your filter is going to be sensitive to the signal-to-noise ratio at every spatial frequency in a way that minimizes the mean squared error. Okay, so remember, this whole thing came from the Bayes linear minimum mean squared error formulation. Right? So in other words, if you have an infinite sequence of data, x, which is related to a signal s, as x equals s plus noise, then the optimal estimate of s at any point in time is given by the output of a filter whose frequency response is exactly this. And this frequency response just tells you how to filter the data according to the spatial frequency at which the SNR is higher or low. Okay? Does this make reasonable sense? Okay, so of course, as you can see, there may be some problems with this expression in the sense that you might, if you just look at this part, you look at the denominator and you think, okay, well, this filter may not be well defined if the power spectrum of x happens to hit 0, right? So if this power spectrum hits 0, then this h of f is going to blow up. But on the other hand, if you look at this here, what you have is pxx is pss plus pw. Now the power spectrum of the noise is what's going to keep this denominator from blowing up. Remember, for instance, if the noise is Gaussian, zero mean with covariance, say sigma squared identity. Now I'm writing this as if it was just a vector, single vector, but really W in this case is an infinitely long sequence of numbers. So if it was an IID sequence of Gaussian random variables with zero mean and variance sigma squared, then the power spectrum for F would be exactly sigma squared. This power spectrum for white noise is exactly the variance of the white noise. So what would happen is that in that case, this here would become sigma squared. and therefore the denominator of this could not be 0. Okay? Now, a problem can arise if the noise variance gets smaller and smaller and smaller. Then it's possible for this guy to have hit 0 someplace, the power spectrum for S to hit 0 someplace, and then you might have an issue. So if the noise variance gets really, really small, the Wiener filter may not be well defined at places where this guy gets close to 0. Okay. All right, also there is a relationship worth pointing out, which is if you look at the finite length version of this, so this filter here. This filter, as I said, is going to be changing. Its impulse response is going to be changing over time. It's a finite impulse response, and it changes over time, right? You can think of this essentially as the equivalent of the sequential least squares estimate, right? Where you use the data as it comes in and you update the result. And therefore, it's not surprising that the impulse response is going to change. Okay? So this equation, on the other hand, or equivalently this equation, which is basically a time-invariant infinite impulse response filter. This is the so-called steady-state version of the equation that we showed you before. Okay? The other one, every time you add a new data point, the filter has to jump up and down to keep up. Right? Here, what you're saying is the filter is going to be fixed. Okay? It's a steady-state filter. It's not going to change. Its coefficients are not going to change. I know exactly how to deal with the data because I have an infinitely long sequence, and therefore I have information about the power spectrum of the signal, power spectrum of the noise, and I know exactly what to do at every frequency, f. Okay. Another thing that's a little puzzling maybe about this kind of expression is, again, remember the data model is this: x of n, s of n, sw of n. Okay? So if you look at this expression, or this one for that matter, you say, okay, the optimal estimate for an infinite length sequence is going to be a filter with this impulse response. But hey, wait a minute, this impulse response actually depends on the power spectrum of the signal, which I'm trying to estimate. Right? So what if I don't know the power spectrum of the signal? Okay? And you don't know necessarily the power spectrum of the signal, right? I mean, if you're starting off, all I'm giving you is this. So what gives? Something has to, some extra information has to be present here. Okay? The important thing to realize is that knowing the power spectrum of the signal is not the same thing as knowing the signal. Okay? The power spectrum of the signal is the magnitude squared of its Fourier transform. And if the signal is random, then there's an expectation in front of it as well. Okay? In other words, you're taking the Fourier transform magnitude and squaring it, so there's no phase information at all. Right? So knowing the power spectrum is not equivalent to knowing the signal itself. It's actually a lot less than knowing the signal itself. Now in practice, what you do is you can in fact estimate the power spectrum of the signal from a bunch of training samples. Okay, so let's say, for example, I give you, the example turns out to be somewhat easier to do with images. Let me give you an example of an image. Let's say this S are pixels from a clean image. Okay? And X are now pixels from a noisy image. And I give you this noisy image, and I ask you to denoise it for me. Okay? And what you're going to do is you're going to try to do this Wiener filter. Well, the problem is you don't know anything about this clean image, right? It's just a photograph that somebody took. So you don't know PSS, right? However, what you can do is you can now go to you can make a database of images with thousands, millions, and people have done this. I'm not just making this up as an example. You make a database of images, thousands, hundreds of thousands of images. None of them with much noise in it. Okay, you try to get the cleanest images you can. Okay? You take those images let's call this huge class of images natural images. Natural because people just pulled out their cameras and took a picture, right? It's not something that somebody set up for this special purpose. It's just a bunch of images. Let's see, collect them from Flickr, okay, or Facebook or whatever. Okay. So now you have this huge collection of images, clean, and now what you're going to do is you're going to estimate the power spectrum of these images, averaged across these hundreds of thousands of images. And now you're going to say, well, okay, if the image that you gave me is probably, on average, something like one of these images that I got. And so I'm going to use the power spectrum that I just estimated in my filter. And people do this all the time. And it turns out, in fact, if you compute the power spectrum of natural images across a huge number of images, what you get is this PSSF decays something like, it's proportional to like 1 over f squared, something like that. Okay, so its power spectrum actually decays quadratically away from DC. So it's used actually quite often for image processing purposes when you know what you're dealing with is a natural image. Now, will this kind of power spectrum work if you're looking at, let's say, a close-up picture of somebody's face? No. That's not a random image. That's a very specific portrait. Okay? But if you're looking at pictures of, somebody took from the street and there's a few people in it, that's probably okay. All right? So the idea is that you can get a large collection of signals, build from them a guess of what the power spectrum for the signal is that you're looking for, and then use that to build this filter. Okay? Okay, so the next set of topics that we're going to work on are going to be non-parametric estimation procedures. And these are very different than the kinds of things that we've been talking about so far, and in some sense, much more general. So let me give you an example of the difference between parametric versus non-parametric estimation. Okay, so suppose you're given a bunch of data as follows. Let's say here's the x-axis, and here's the y-axis. And let's say I give you a bunch of data points like this. Okay? An example of a parametric estimation is to say, this data looks like it might have come from a line. Okay? So what I'm going to do is I'm going to fit the best line that I can across this data. Okay, so what I'm going to say is I'm going to assume a model. So let's say at each one of these points here, this is let's say xi, and this is the corresponding yi. Okay, so this is a position, and that's a value. So you make a model. You say, okay, yi is equal to mxi plus b plus, say, wi, when this is kind of error. Okay, so the point is this part here, this is the equation of a line, right? And the idea is that m and b are not known. This is the slope, and that's the intercept for this line. I don't know what they are. So what I'm going to do is I'm going to estimate these coefficients m and b. There's lots of different ways to do it. One of them would be to do least squares, for example. Okay? So I take all of my y's, and I stack them into a vector, say y1 through n. Okay? And now I have y equals, there's two unknown parameters, m and b, plus w. And in here, I'm going to have x1, x2, so on, xn. And here I'm going to have 1, 1, so on. Okay? So now I have this h, and this is theta, and I might do least squares. So theta hat would be h transpose h inverse h transpose y. Okay? And then these parameters, which are m hat and b hat, they would define a line, y equals m hat x plus b hat. And that's the equation of this line. Okay, so this is a classic example of a parametric fitting problem. Now, I simply chose, by just eyeballing this, I simply chose a linear equation to fit to this. But you can fit anything you want. You can fit quadratic, you can fit an nth order polynomial to this, okay? And that might be much more wiggly, but then it might go through all the data points in a very nice and clean way. Okay. So, what you did is you described your fitting problem with just a couple of parameters, and then if I asked you to predict for me, given this data, what would be the value of the data point, let's say at a position where I didn't have a sample, then that prediction would be this point here, right? So suppose I wanted you to predict what would be y at some x star, right? Let's say x star is over there. Okay, so what would this be? This would be m hat x star plus b hat, right? Okay, and this would be a good predictor based on the least squares criterion that I gave. Okay. So the bottom line here is that the parametric methods are global. So what do I mean by global? I mean a couple of parameters completely determine the overall global behavior of this fit. Okay? Now the problem with these things is that global methods like this tend to be rather sensitive to unexpected errors. So suppose instead of the data points being like this, suppose this one was way out there. Okay? Suppose it was just so far wrong that it was off the page. Okay? Now what would happen to this equation of this line? It wouldn't be like this anymore, right? It would probably be pushed like that, just because of that one data point. Okay? So in other words, that one data point can affect the estimate of the parameters. And so what you might want is you might want a fit that is more flexible. In other words, in places where the data looks like a line, it fits a line. In places where the fit doesn't look like a line, it doesn't fit a line. Okay? So then you might say, okay, I'm going to break the data up into two pieces. The piece that I think looks like a line, and then there I'm going to fit a line. The piece that doesn't look like a line, and in that area I'm going to fit something else, like let's say quadratic or a cubic or something else. Okay? And now we can take that idea much further. So why divide the data into two pieces? Let's divide the data into n pieces. Okay? And in every little region, let me fit a different function. Okay? In fact, n doesn't even have to be finite. I can fit a local function anywhere that I want, given some number of data points around it. Okay? That's the basic idea of non-parametric estimation. You don't rely on a single function to fit all the data. You basically become much more flexible, and what's a little weird about it is why we call it non-parametric. Right? I mean, it seems like we're using more and more parameters, so why are we calling it non-parametric? This is maybe an unfortunate choice of words, but it was something that was used many years ago when these techniques were invented in statistics, and the name has stuck. So it's not my choice to use it, it's just a word that's used. But why it's used is because if you take this idea to its logical extreme, in other words, instead of dividing the data into 2 pieces and 3 pieces or whatever, you just kind of say, you know what, at every point I'm just going to fit a function, and then I'm going to connect these dots together to get a continuous curve. What you're doing is you're essentially using infinitely many parameters, right? So then when you're doing that, there's no point in talking about parameters anymore, right? So that's why they call it non-parametric, because you're using so many parameters that it just doesn't make any sense to talk about specific parameters anymore. I know it's kind of a weird word to use, but that's the origin of it. So let's see how that works. How does non-parametric estimation work? All right, so I'm going to give you a very general description of non-parametric estimation, and then I'm going to make it very specific with a particular choice of, with a particular way of doing it. So let's be very general for the time being. Let's say, again, you have X and Y, and you have a bunch of samples here, and they might be, some bizarre shapes. Okay? And so at each one of these points you have, xi and yi. And so the idea here is you write a model that looks like this. Yi equals z of xi plus, let's say, some error ei. Okay? Now this function z, we call this the regression function. Okay, again, that's another unusual word. To regress means to go back, right? So the idea is that you're choosing this function in such a way that at every point you can go back to this definition of this function and predict what the value of the function would be at a particular point. Okay, so for this framework, what you're going to do is at any given point, you're going to estimate the value of the function, and let's say if I is equal to 1 to n. Okay? So now, my job is I'm going to pick some x, and it can be anywhere. Let's say I pick x to be over here. Let me call this xj. Okay? Now, if I go up here, there's no sample there, right? There's no red mark. So I have no idea what the value of the function at this point would be. I don't even have a measurement there. Okay? But somehow, because the nearby values look like they have some shape, it's kind of going up here, I'm gonna think, well, it's probably gonna come out here, right? Okay, so how do I come up with this estimate? To be more specific, I'm not trying to estimate all the points on the curve. I'm just trying to estimate that one point for the specific xj that I'm interested in. Okay? So given yi for I equals 1 to n, what I want is to estimate z of xj for some xj. Now this xj might be one of the xi's or it might not. It really doesn't matter. Okay? So how do we do this? Okay, so here's a very simple framework for doing this. Let me write a least squares function like this. So let me write sum I equals 1 to n of yi minus z of xj squared. Okay? So what I've done is I've said, well, I'm just going to pick xj. Sorry, I'm going to pick z at this point, this black dot, in such a way that its distance from the points around it is not too far in the least square sense. Now, when I say I equals 1 through n, you don't have to use all the i's either. You can just use some window. Okay, you can just say, well, I'm just going to go 2 samples to the left and 2 samples to the right, and that's all I'm going to use. In which case, you wouldn't use I equals 1 through n. You would use I equals, whatever, 4 indices, 2 to the left and 2 to the right. Okay, completely up to you. I'm just writing in the most general way possible. Okay. All right. So if you look at this, if you minimize this over z of xj, it's very simple. This is just the least squares problem, and the solution to this is the estimate of the value of the function at this point, xj, is simply 1 over n sum of yi. I equals 1 over n. Okay? It's not hard to see. All you have to do is you differentiate this with respect to z of xj. It's a scalar. Set it equal to 0, solve, and what you get is this. Okay. Now this is not very exciting. Okay, because what you're saying is I'm going to take, let's say, some samples to the left and the right of it, and z is just going to be some average. An average with 1 over n a weight in front of each one of the data points. So another way to write this is put the 1 over n inside. Then you're just averaging with equal weights. Okay. But then we might think, if you're going to average, why give the same weight to all of your data? In other words, if I'm interested only in this data point, why should this data far away have the same amount of influence as this data point, which is right next to it? Okay? The data that's right next to it should have more influence, right? So it seems kind of ridiculous to have 1 over n in front of it, right? So instead of doing this least squares, what we do is weighted least squares. Okay? And the weights are simply going to give heavier influence to stuff that's nearby and less influence to stuff that's far away. And that's the following formulation. So now you just rewrite this I equals 1 to n, yi minus z of xj squared times k of xi and xj. And this k is what we call a kernel. Okay, what does this kernel do? This kernel simply measures the distance between a sample at xi and a sample at xj. It just measures the distance between the point xi and xj, and if they're near, it gives a high weight. If they're far away, it gives a low weight. So what this is going to look like is it's going to look like some function like this. Okay? And it's going to be centered around 0, which means that if these 2 points are right next to each other or right on top of each other, then that point gets the highest weight. Okay? Now, what do you choose for this kernel? You can choose just about any function you like, as long as it satisfies a few simple properties. One, you probably don't want this function to have multiple bumps, right? You want it to have one peak. So it's unimodal. Second, as you go farther and farther away, you want it to decay, right? So you want it to be decaying. And third, you probably want it to be positive, right? You don't want negative numbers necessarily directly in here, because what you're doing is you're measuring distances. Okay? Okay, so is this clear so far? All right, so
is this basically a piecewise fit?
it is a piecewise fit. It's actually more than a piecewise fit. It's a pointwise fit. Okay, because I'm just estimating z of xj, which is 1 point. So I'm not fitting it piece of the curve. I'm fitting just one point. I'm using an expression that looks like a whole curve, but all in the end, I'm just using one point from that curve at every point xj.
I mean, the way I'm looking at this right now is it's more or less like a linear model where you, in your H matrix, the different columns have mass that's slowly moving down the rows.
Right, so that's what I'm going to write down next. So maybe that'll correspond to your intuition. Let me just write it down, and then if it doesn't make sense, then I'll go back over it. Okay, so let's just rewrite this weighted least squares problem. Okay, so let me just write down z hat of xj is going to be the argmin over xj of zxj of sum yi minus zxj squared I equals 1 to n k xi xj. Okay, so this is exactly what I just wrote in the previous page. But now let me make a few definitions. I'm going to take all the data points y and write them into a vector. So y1 through yn. This model here is just a constant, right? This is just a single number. So if I write these, if I wanted to write a vector z for this would just be z of xj times a vector of 1s. 1, 1. Right? So this is just z of xj times, I'm going to write it like this bold 1. Okay, so vector of 1s with n elements in it. And then for the weights, I'm going to define a matrix, capital K sub j, and this is going to be a diagonal matrix. Well, let me just write it out. It's a diagonal matrix with K, x1, xj, through K, xn, xj, and 0 here. Okay? So with these definitions in place, then my least squares problem, this quadratic least squares problem, becomes y minus zxj times this 1 transpose kj y minus z of xj times 1. Okay? So you can think of this as y minus h times theta. H here is just a single vector of 1s. Okay? And your unknown is this theta. So this would be like y equals h theta plus error. And so your h is this guy. Your theta is that guy. Okay, so it's just like a least squares, standard least squares problem. Okay? All right, so if we solve this, if we just minimize this, what do we get? So from here, you get z of xj hat equals, minimize the least squares criterion, you get 1 transpose kj times 1. This is like h transpose h inverse, okay? And then 1 transpose kj y. Okay, this is just the least squares formula. Now let's write it out in more simple form. If you multiply everything out, remember this guy here is 1 transpose kj1. This is just a scalar. And so is that. Okay? So what ends up happening is z hat xj becomes sum over I of k xi xj divided by sum k xi xj over I times yi. Okay? Does this make sense? all you have to do is multiply this out to see that this is the case. Okay, so what is this? We can write this as, in a simple, simpler way, as say wij times yi, where these coefficients w are simply these guys. Okay? So what's happened is the estimate at xj is still a linear combination of the values of y, except that the different terms now don't have a weight of 1 over n in front of them. They have a weight in front of them which is proportional to how far away the data sample at xi is from the position that you're interested in, which is xj. Does this make sense? So let's take a quick look back at this. Okay? Here, remember, without the weights, k, without the kernel k, the weights were all 1 over n in front of this guy. Now, instead of 1 over n, the weights are this. And k, of course, was related to how far away the samples were from your position of interest. So all that's happened is that 1 over n has been replaced by higher weights given to samples that are closer and lower weights to samples that are far away. Okay? Another interesting aspect of this is that these weights, just like 1 over n that you had n samples, the weights in front of them were 1 over n. You summed up n 1 over n's, you got 1, right? Here the same thing is true. If you take these weights and you sum all of them, all the ones in front of yi, you get 1. So sum of these weights is 1. Okay, so what this does is it automatically produces weights that give high and low importance to where you are. Another way that this whole thing has been referred to in the literature is moving least squares. Right, that's all it is. You've got this curve. Okay, so you can define a window around here. Let's say 2 samples before and 2 samples after. Write down exactly this least squares formulation with weights. You solve for this guy. And now let's say instead of that guy, you want another point, let's say over here. And this is what you want to solve for. So what you do is you take your window and just move it around. Okay, now you've got another least squares problem to solve. The weights are going to be different because this point may not be as close to this guy as this one was to that guy. Okay? So what you end up with is a bunch of linear filters. These are linear combinations of data with non-trivial weights. And when I say non-trivial weights, I'm referring to 1 over n as a trivial weight, right? It's just the same for all the data points. The other thing that's interesting about this is that these are shift-varying filters, right? So if you remember just the definition of a shift-invariant filter, shift-invariant filter is one where if you move, the coefficients don't change. Here, if you move, the coefficients change. Depending on how close xj is to the next data point, you get different weights. So these are linear shift-varying filters. Okay? And so then if you have some crazy behavior in your data, you can locally capture that crazy behavior as closely as you want. All right, so let me give you another specific way in which, so this was very general, right? So linear combination of the data. In fact, this is called a convex combination of data because Wij are all positive and bigger than or equal to 0, and the sum of Wij over I is equal to 1. So it's a bunch of positive coefficients and they sum up to 1. This is just the notation for that, or the term for that is that it's a convex combination of the data. Okay. Another name for this is that it's called zeroth order regression. Okay? It's called zeroth order because these coefficients can never be negative. Now you might imagine there may be some scenarios in which having negative coefficients would be helpful. And so how do we generalize this scenario so that you might also be able to consider negative coefficients? So let me show you a slightly different way of looking at all of this. Okay, so remember z of x has sort of an undetermined form. Okay, we haven't specified what kind of functional form it's going to have. All we've said is that at some point it's going to be some constant value and we're going to estimate it. So the next thing to do is to say, well, at this given point that I'm interested in, the function is not just some constant. I'm going to do the parametric thing, except that I'm just going to do it very locally. Instead of just saying z of xj is some number, I'm going to say z of xj is a point on a line. And what I'm going to do is I'm going to estimate the equation of that line and then read off what the value of the function is at the point of interest. And then you can generalize it and say locally, instead of saying it's a line, I'm going to say it's a quadratic, but only locally. Okay? So this is how we proceed. We say, okay, even though z has an undetermined form, what we're going to do is we're going to assume that z of x is locally smooth. It means, all this means is that you can write z of x as a Taylor series expansion. Okay? That's all. So for instance, we can write, say, z of xj is z of x for any x plus z prime of x times x minus xj plus 1 over 2 factorial z double prime of x, x minus xj squared, and so on. Right? Okay, so this says that near xj, the function, I'm just going to assume that the function is smooth near xj. Okay, so let me write this in a different way. Now, I don't know this, right? And I don't know this. So I'm going to call these, I'm going to give them names. The first one is going to be called beta 0. The second one is going to be called beta 1, x minus xj. And the next one is going to be beta 2, and so on. Okay? So this is beta 2, beta 1, beta 0. Okay? So now, instead of this least squares, which was yi minus zxj squared with k of xi xj, instead of this, I'm going to do the following. Sum I equals 1 to n yi minus, oops, sorry. Well, I'm going to plug this in here. Okay? Instead of just using zxj, I'm going to use this Taylor series expansion. So then this becomes beta 0 plus beta 1 x minus xj plus beta 2 x minus xj squared, and so on. Squared k xi xj. Okay? So what's the difference between this and this? If I considered the Taylor series expansion only for the constant term, then I would just have that, which is identical to what I had before. Okay? However, what I've done now is I've said that the function is locally like something that has some additional detail in it, as opposed to just being a constant. So what that does now is it allows me to fit a whole bunch of other coefficients. Okay? And remember, this is still a local least squares problem. In other words, if I move to another window, another position where I'm interested in, I'm going to estimate these coefficients all over again. Okay? Now, when I do this, as a result of this, I minimize this over the betas. Okay? And what I get is a bunch of estimates, beta 0 hat, beta 1 hat, beta 2 hat, and so on. Okay. Now typically, by the way, we don't do this with many, many terms. If you do it with no terms, just beta 0, then it's that. If you do it with one term, it's called linear regression. If you do it with two terms, it's called quadratic regression, okay, or second order regression, and so on. So typically we stop here. Stop here. Okay. Now, if all you're interested in is the value of the function, then these other coefficients you don't need. Okay? So then your estimate simply becomes z hat of xj equals beta 0 hat. Okay? And you can then ignore the rest of these numbers, which then probably elicits the question, then why'd you bother with this? If you're going to throw away these other coefficients, why do you bother? Okay. It's very important to realize that the beta 0 that you get by doing this, which is you estimate all the betas and you throw the other ones away, this beta 0 hat is very different than the estimate that you would have gotten if you simply used only one of the terms. Okay? And the reason why it's different is because in one case, you're assuming that the signal is a constant. Whereas in the next case, this one, you're assuming that the signal is actually locally a line, or locally a quadratic, or locally a cubic. You're fitting that function, and then you're keeping the value of that cubic, or that quadratic, or that line at that position. So this beta hat 0 is not the same thing as the estimate that you got before. Okay? I can show you a picture of how these two are different. Maybe that'll be a little bit more sort of illuminating. So let me show you. Okay. Well, let's start with this. Okay. By the way, from an intuitive point of view, this estimation is really very, very simple. This is called kernel regression, and this is very simple. What it does is wherever you have a data point, you're putting down a kernel. Okay? If you want to simultaneously estimate the values of the function everywhere, then the way you do it is the following. Every place where you have a data point, on top of it, you put a Gaussian, just like whatever shape you want to pick for the kernel. Okay? So now you have a bunch of overlapping kernels, right? All you do is you literally sum them with weights given by how big the data point is, and then this automatically gives weights to how close the other data points are. And then what that gives you is it gives you a curve that you fit. Okay? But so now take a look at what happens here if you estimate a 0th order model. In other words, all you're doing is that first estimate that I showed you, where you only use the beta 0, you don't even bother estimating the other ones. Okay? So let's say this was the true curve. Okay? Here, at some point x, this is our xj, right? So this is like your xj. At this xj, you want to estimate this point. Locally, you're going to assume that this curve is a constant. You set the least squares problem up, which is just this. Okay? And you get an estimate, which is this guy here. Okay, so this is the estimate that you come up with. Okay? Not necessarily very good, right? It's not very near the original curve that you started off with. Now, let's go to the linear model. So now what you're going to do is you're going to take this z of xj, and write it as a linear model, and fit the coefficients of that linear model, and then keep beta 0 hat. Now what's going to happen is you're going to allow this fit to be a line, and you're going to fit beta 0 and beta 1, keep beta 0, throw away beta 1, and what you're going to get is this point instead. Okay? Now let's go to quadratic and see what happens. Now if you go to quadratic, now you have 3 coefficients. You can estimate all 3, you're going to throw these 2 away, keep that one, and now you get this value. Look how much closer to the true curve you got. Okay? Why? Because when you had a constant, you were constrained as to the local shape of the curve. Here, you have more degrees of freedom. Of course, having more degrees of freedom is also a little bit dangerous, because if these data values were not really changing so much, but if the data values were changing because of noise, then if you keep going to higher and higher order polynomial approximations, then what's going to happen is you're going to end up fitting to noise. Right? You're going to think of noise as signal, and you're going to make a very wiggly looking curve, which is really not indicative of the true nature of the data that you have, but it's just wiggling because you went to a very high order regression. So what ends up happening basically is that you are, by deciding whether you want to do a higher order regression or not, what you're doing is you're trading off bias against variance. Okay? So the higher order you go to, the more your curve that you estimate is going to wiggle. In other words, it's going to have a higher variance. But it's going to have lower bias. In other words, at places where you didn't have noise, you would get exactly the right answer. Okay? You can expect the bias to be very close to 0. Okay? When there's no noise, but that's fine. However, when there's noise, you're going to be oscillating a lot. On the other hand, if you keep yourself to a very, very low order regression, like even 0th order, then what you're going to get is you're naturally going to get something that's a very smooth looking curve. So its variance is low, but the curve may not be very close to the true curve that you started off with, so its bias is high. Okay? So just like any other estimator that is going to estimate the shape of this curve, this non-parametric method also has a bias variance trade-off. In this case, you can think of it as the order of the regression determining the bias. Okay? Another way to think about the order of the bias variance trade-off is in this problem here, or in this one, we are going to choose this kernel, right? Let's say I pick it to be a Gaussian. This Gaussian has some parameters, okay? Well, the mean is not really a parameter because that's going to be centered at my position of interest. But the variance of this Gaussian is a parameter, okay? If you pick the variance of this Gaussian to be very, very small, then these bumps, instead of looking like this, these bumps would look like that. In the extreme, if you pick the variance to be very, very small, then the bumps don't interact with each other at all. Then the estimate that you come up with wiggles a lot. Okay? On the other hand, if you pick the variance of these Gaussians to be very large, then instead of this, you might be looking at things that look like that. And then these Gaussians overlap with each other a great deal, which means you get more smoothing. Okay? So you can keep the order of the regression fixed, let's say at 0 or 1 or 2, but then change the variance on the kernel, and that also gives you another mechanism for trading off bias against variance. Okay? So we'll talk a little bit more about this next time, but I think you should really try to make sure that you understand what's going on with these non-parametric estimators, because they, in practical situations where you typically don't have a model for the data, these are really the only ways to go. And in fact, in terms of our field, in image processing, these types of non-parametric estimators are the ones that really work. Okay? And in the last 10 years or so, both in machine vision, in computer vision, and also in image processing, non-parametric methods have become the standard thing to do. Okay, so we will stop here for today. And please turn in whatever is due.
So, there's just whether or not I'm viewing this kernel regression properly. So, the way I'm saying that is, say your z function is a say a linear combination of some parameter times a known function. Say f1 of x, that's defined only on a given boundary. And I guess
in a window.
Yeah, in a window. And then you're summing a whole bunch of them.
Right.
So then, whenever you're doing your so then your signal will be some H matrix, which will have some values, then 0, a 0, some value, 0, and so forth.
Okay.
And then you have your parameters.
So these are what you're calling the betas? If they don't have beta 2, whatever?
I guess not exactly, since I guess the local
The local model.
Yeah, the local model will be encompassed in this f of I, which I guess is assumed in...
So I don't understand what you're writing. What's x? X is, in this notation,
Your
my
signal.
x was, no, in this notation my x was positions, right? I mean, you're using x here and x there. Okay, right, so that's what you measured. Y is what you've measured.
Right, so y is... Right, y is what you measured, then these values here are each f of x.
Right, okay.
f1, f2, and so forth. Then I guess you would do a parameter fit for these different thetas, and then just to get an estimate for an X that has not been observed, simply plug in the X into this, and
Right.
it'll basically take, it'll fit it to the nearest function.
Right. Well, it's a little bit different because what you're doing is, let's forget for a second the local model, right? Let's just say we do the simplest thing in the 0th order case. In other words, you're assuming that the function is just a constant. Then, all you're doing is estimating that constant. So then, in that local window, then it doesn't matter where you look. Your estimate is always going to be that same constant value. You see what I mean?
Okay, so then that's basically fitting out a whole bunch of, I guess, pi functions.
What's pi function?
Pulse. And that's how it was defined, and it basically says that X is around. That's one. It's a variation of the step function.
Yeah, you just moved it over. Okay, so, all right, so there's two things going on here. One is that you're going to estimate the form of the local function. So in this case, we decided it was going to be constant, right? And then once you've got an estimate of the function, you can think of that estimate as being composed of these bumps. The bumps that it's composed of, in the case where you pick the kernel to be a Gaussian, then those bumps are going to be Gaussians. Do you understand what I mean?
Yeah.
So no matter what your local model is, whether it's linear or quadratic or whatever, forget about that for a second. Let's just stick with the constant case, right? So I'm not using the Taylor series expansion. Okay? So in that case, you do this fit. You could do this fit at infinitely many points, right? And then you would get this smooth curve.
Right.
And then you think to yourself, well, how did this curve come out so smooth? Right? I mean, because I fit one point at a time, but somehow this curve came out very smooth. Well, the bottom line is this curve is nothing but a linear combination of a bunch of bumps.
Yeah.
And the bumps are the Gaussians that you picked. Okay?
Right. So then, yeah, I guess these f of
eventually Z becomes, these F's are nothing but the kernel functions that you picked.
Okay.
Okay?
And they're defined to be local so that you don't iterate on the whole data.
Exactly. That's right. And so now that you've understood that, now we can take the next intellectual leap. Now what happens if instead of the 0th order regression, you do, let's say, a 1st order regression? So now locally, you're going to assume that the constant function is not constant, the function is a line. Can you still say that this is a linear combination of these f's? Yes, you can, except that these f's are a little different now. So it's not just the bumps now, it's some modified, massaged version of the bumps. Okay? So by going simply from a constant local model to a constant linear or quadratic model, you don't change the linear combination form. Coefficients become different, and these functions become slightly different. They become different versions. Like, for instance, if you do a linear fit locally, then these functions, instead of just being the Gaussians, they become the Gaussian and various differentiated versions of the Gaussian. So you're not just computing a linear combination of Gaussians, you're computing a linear combination of the Gaussians and their derivatives. And that's why the coefficients can now go negative, right? And now if the local model, instead of being constant, becomes quadratic, you're using 2nd order derivatives, right? So now this linear combination becomes a linear combination of Gaussians, derivatives of Gaussians, and 2nd derivatives of Gaussians, and so on. Okay? There's like 1,001 different ways to look at this. You've picked up on one that is very intuitive, and that's fine. That's a perfectly reasonable way to look at it. And the other interesting thing about this is that, you know, the local approximation that we did, we use the Taylor series, right?
Yeah.
You don't have to. You can use any local approximation you like. The formulation is exactly the same. Okay? The difference is, when you use the Taylor series, the interpretation of this sum is simple. It's the sum of Gaussians and derivatives of Gaussians and so on and so forth.
Yeah.
If you use a different basis to do your expansion, then this becomes the sum of the basis functions, linear combination of basis functions, and then some weird interaction of the basis functions together. Like you can use a wavelet if you want, for instance. Then you get the higher order interacting terms of those wavelet coefficients. So you don't need to worry about that. I'm just saying this framework is at the same time so simple. It's all a bunch of least squares problems, right? But at the same time, it's incredibly powerful because you can do any kind of local expansion. You can use any number of terms you want. The bump function that you use doesn't have to be a Gaussian. It can be anything you like. In fact, if you pick the bump not to be a Gaussian, but to be a square like you drew here, what you get is basically what's called a histogram estimate. Okay? So what you do is you go into a window and you count how many samples are nearby, and based on that you estimate what the value of the function is. Okay? And if you pick these bumps, these square bumps to be big enough, then they all interact with each other. If you pick them not to interact with each other, then they don't interact with each other. So you can do just about anything you want. And therefore it's a exceedingly powerful way of doing things. Especially for signals that are so complicated that you can't easily model them globally. Right? Here, this says, it doesn't really matter what the global model of the signal is. I don't care. All I'm going to do is I'm going to build a local model of the signal and slowly move it around and just keep doing this least squares estimation. And somehow, the whole framework is going to guarantee that these points are going to fit together in a very smooth way. Because implicitly, what I'm doing is computing a linear combination of a bunch of smooth functions.
Right. So then the whole idea is basically to have these functions be localized so that you don't solve the entire matrix.
Exactly. Yeah, the functions are localized, but they do interact with each other.
On a local level.
On a local level, exactly.
But once you go past your window of interest, you don't need to worry about solving that part of the matrix.
That's right. That's right. So you just move on, and you do instead of. So what's the non-parametric situation? The non-parametric situation is one really big least squares problem, right? So what this is a bunch of little least squares problems that somehow fit together in a very tidy way. You don't have to worry about what happens when you go from one window to the next, because of the smoothness of these bumps, everything works out.